Hello, everybody. Welcome to this conference. Thank you all for joining us. I'll pass the word to our host today, Professor Filipe Santos.
Hello, everyone. Welcome to the Knowledge Conferences at Católica-Lisbon, our regular moment of sharing the latest knowledge and insights by our faculty and invited guests. It's a great pleasure today to focus on a theme that is very important and very popular these days, but also very complex, which is the area of in data science, artificial intelligence, and specifically deep learning, how to make automatic learning. This is an area that the school has invested a lot in the last few years. We have, I would say, an outstanding faculty group in data science, which is very international as well, and has some faculty members who are world-class, both Portuguese and international. And we are doing a lot of things. One of those outstanding faculty members, despite his young age, and he joined us just 2 years ago, but has done already outstanding work and top-level publications, is Joran Gebreitz, who is giving us his insights and sharing on deep learning. He will present for about 40 minutes his latest works and insights, and we'll have a chance for a few questions at the end. And without further ado, I'll pass the floor to Joran. Thanks for joining us and sharing your knowledge and insights with our community, Joran.
Thank you so much for the introduction. So I hope my screen is being shared now.
Yes, perfect.
The audio is working well. Okay, that's fantastic. Okay, welcome everyone. Thank you for the amazing introduction. So indeed, like I'm a second-year faculty member here at Católica, but well, I had a great introduction. So let me just get started by talking about the topic of today, deep learning, and specifically, I want to focus a little bit on deep reinforcement learning, which is something I'm heavily involved in my my own research. So deep learning today has really found its way into our daily lives. So a lot of us use Face ID to open their phones. Basically, your phone is recognizing who you are, and based on that, based on the data that it gets, it knows who you are. It's something that 10 years ago was unthinkable. Many of you may also be using HomePods at home, which are devices that you can talk to. They recognize what you're saying, and based on that, they can take a certain action. So a lot of devices use deep learning today, even though we may not know that this technique is actually being used. We are actually already using it and finding it in a lot of applications. A second example are self-driving cars. So cars are not fully self-driving yet, but we are getting really far, right? So if you look at Tesla, then well, the core software that is currently being used in the self-driving vehicles is a neural network. So it's this neural network that is being used that the car is using to recognize what is going on around the car, in order to then drive by itself. So deep learning has clearly found its way into several applications. But the question today will be, okay, what is deep learning? Because I think many of you are here to learn more about the technique. And some of you may know which applications it's currently being used in. Some of you may already be using it in your jobs or your companies. But I want to start with a high-level overview of what is deep learning actually. And by the way, before I really kickstart the remaining part of the presentation, I also want to say, if you want to interrupt me or have any questions during the talk, feel free to just post the questions in the chat, and I will take them along the way. So what is deep learning? Well, just to position it a little bit, so it is indeed, as was mentioned before, a part of artificial intelligence and data science. So artificial intelligence itself is, really just a big name for a lot of intelligent behavior. So as long as your machine is intelligent, then we call this artificial intelligence. Now, recently, a lot of progress has been made in machine learning, and this is a smaller subset of artificial intelligence, where we don't explicitly program a machine on what to do, but we just reward it for good behavior, right? So we're going to see examples of what that is. But for example, if you go back to the example of Face ID, image recognition, there we cannot possibly code based on all the pixels of the picture. If this happens, then you have to, then it will be the person A, or if this happens, then it will be person B. That is just simply not possible. So we need to have a different way of programming. So we use a learning approach to learn to detect patterns in order to make decisions. Now, within this machine learning, there is deep learning. So deep learning is just a subset of machine learning where we use neural networks to learn. Neural networks, some people say it's inspired by the brain, but the idea is that we use a big neural network, and I'm going to show you what that is, in order to learn something. So it resembles a little bit how a human learns. But this is really what has, the performance of deep learning has increased drastically during the last decade. And this is really, so a lot of applications are now using deep learning. Now, within machine learning, we also have three different branches of algorithms. The first branch is supervised learning, where we have a labeled data set. So a data set with, for example, millions of images with labels. So for example, if we have a lot of images of traffic, where we have traffic lights, we have other cars, then we need to have this data set with labeled images, and then we train a deep learning network to try to recognize these pictures. So we need a labeled data set to do that. And of course, once we have then a trained neural network, we can then reapply this methodology, the deep neural network, on a data set where it hasn't been trained on. The second branch is unsupervised learning, where we don't have labels, but we try to cluster our data. Now, this is not the scope of today, so I'm not going to spend too much time on this part. But the third branch, reinforcement learning, is really getting a lot of attention these days. And this is where we don't try to recognize, okay, what is the label, but we try, through trial and error, we try to develop a certain policy. So a certain policy, it's going to become clear what this is, but it's really, for example, a robot that is learning how to walk. Then, the fact that the robot is walking, this is kind of a policy. And just like a kid is learning through trial and error, we're going to let our machine learning algorithm also learn through trial and error in a reinforcement learning framework. So why am I saying all of this? Well, because a lot of the applications today of deep learning are within supervised learning, where we have labeled data sets and, for example, a lot of images or a lot of text, text that we learn what is on the images, or we learn what is on the text. But in fact, you can apply deep learning across these three areas of machine learning. And today I want to zoom a little bit in on the last part. So on this reinforcement learning part, where several breakthroughs the last years have been made. And that's also really where I'm currently focusing my research on. So while supervised learning, deep supervised learning has found its way into applications, this deep reinforcement learning is somewhere getting applied very slowly, but it is a little bit the future. At least I am positive that there is going to be an impact. Okay, so what is deep learning? It is essentially a black box function, right? So it's a function where you put something in and you get something out, and what is happening within that function, that is something very complex, right? So this is this neural network that I'm going to explain. But essentially, it is a function. Now, a neural network is not new. So if we go back all the way down to the 50s, so I was not around, and probably many of you neither, then Professor Rosenblatt at Cornell was actually building this machine. And it's with these punch cards. I'm not sure whether some people are familiar with punch cards. Some of you may be. I think my father knows what it is. I've never seen it in my life. And the first neural network was actually not coded in software like we code it today, but it was really a machine where we had to fill in some of these holes. Then we could process images through that machine, and images were then also with this punch card made. And using that machine, we could actually detect what was on the picture. And so here you see the perceptron, which is this machine. And we have some input variables. For example, this could be a picture, or this could be some features of several animals. What we're going to do is these inputs, we're going to multiply them by weights, and these weights in this machine were not coded, but they were actually put in there. We multiply the inputs times the weights, we sum everything up, and then we pass it through what we call an activation function. That means, for example, okay, if the number is larger than 0 here, then we're going to forward the information, and otherwise not. And this can create, for example, a classifier where we can, it's a linear classifier where we can distinguish between objects in a data set. So since the 50s, we have been doing this. This was, of course, absolutely not what we are doing now, but this is kind of the start of deep learning if you really trace it back to the roots. Now, today, of course, we are a lot further. So we have very, very big neural networks, and this is a nice visual, I think. So what we see here on the left side is the MNIST data set. So it is a data set with a lot of handwritten digits, so going from 0 to 9. So we have 10 different possibilities. And what you see here is that this image, for example, the letter 9, is for a computer, it's a combination of pixels, right? And a pixel we can represent by a numerical value. For example, a 0 would be black, a 1 would be white, and maybe if it's on the grayscale between 0 and 1, then we can also have fractional numbers. Those pixels we can feed to the first layer of such a neural network, and you see based on the color that is becoming greener here, that means that the number is higher, gets multiplied by all these weights in the network. There will be activation functions between the layers as well. And this process can repeat itself several times until in the end, we have 10 numbers, and the number with the highest value will then be the recommendation of the algorithm, right? So the idea is that if we set those weights, all these white edges to the correct numbers, then we create a deep learning network that is actually able to recognize which digit is being proposed to the model, okay? So this is a basic representation of a neural network. We have neural nets in all kinds of flavors, but this is really just a very simple, fully connected layer with a fully connected network with 2 hidden layers. So there's 2 hidden layers here in the middle. Okay, now you may think, okay, that sounds very fancy. Now, but why are we really doing this? Well, a very nice and theorem that was proven is that if we have a neural network with a very, very big layer, right, so a very wide layer, then there's this universal approximation theorem that tells us that effectively we can almost approximate anything, right? So you could with that simple function, you can approximate anything as long as you make the network very, very big. So this is very powerful. So it tells us like, okay, it is a function, but a very powerful function. So, we can recognize pictures, we can recognize voice, but there's abundance of other things that we may be able to do with these neural networks. Now, that's the nice part of the theorem. The downside is that it doesn't tell us anything on how to set the weights of such a neural network, right? So it's a theoretical result. Now, getting it to be to really apply it in practice is a lot harder. But then again, we also have a lot of breakthroughs recently that seem to really have cracked the code. Like we have some breakthroughs that really make it work well these days. So that's a bit what I want to talk about now. So why now, right? So as I said, okay, since the 50s, we have been working on this. There is some really strong researchers that have been working in the 80s and the 90s, a lot on neural networks. But then why is deep learning such a fuss now? And why do we find it in applications, etc.? And there's really 3 reasons for this. The first reason is that, well, it appears that if you have a lot of data, that deep learning works very well. So what we see on this plot is that the performance really goes up the more data you have. And while it is not really true for the older algorithms, where the performance typically tends to stagnate after a while, we see that deep learning, if you feed it more data, it really continues to perform better. And it's a very stylized representation, but it actually holds true. This also causes some problems because there are companies with a lot of data, the so-called industry giants. Think of the Googles and the Amazons of this world. And the quality gap in the products that they have in comparison to small and medium-sized companies is simply because they have so much data, right? So, but the access of data now is we have so much more data now than we used to have, and that's really reason number one why deep learning is popular now and it wasn't so popular 20 years ago. So that's reason one. Reason two is the cloud. So we have a lot of cloud computation available, and this simply means, like, rather than having one computer on which you do the computation, which is already a lot more than we had in the 50s when we had this big machine. Right now we have, everyone has their own computer, but running such a neural network and training such a neural network with the we have to do a lot of operations, and that is very hard on just a small computer. But what can we do? Well, we can simply stack computers next to each other and use a lot of machines to parallelize the computations and to do things faster. And the cloud is simply that. It is just a very a lot of computers, a lot of CPUs, a lot of GPUs, a lot of processors, and everything else you want. And we can buy on the spot some capacity if we need it. And rather than training our models on our computers, we can actually do it in the cloud where we have so much more capacity available. Also, we have dedicated hardware that has been developed for several applications. For example, graphical cards have been used or originally developed for the gaming industry. But now they tend to be very, very helpful for the deep learning community, because we have to do, just like in gaming, we have to do matrix multiplications. And these matrix multiplications really lend themselves well to parallel computation, which is exactly what a GPU is doing. So if you had seen this hype coming, and I've been teaching this since a couple of years, this is a slide from 2019 when I started showing this. This is the stock price of NVIDIA. 2019 was 144 or 155 here, US dollars, because they make the hardware for deep learning. There was a crash here. Usually I ask, like, why is this? Well, because in 2018, the GPUs were also used for something else, namely for Bitcoin mining. Bitcoin crashed at that time, so that's why there was a huge crash. Nevertheless, I always try to look, before I teach this or I give a presentation, I try to look up what the current stock price of NVIDIA is. And it is at $259 now. So you see that, it really grew a lot. You could say, okay, investing in GPUs and CPUs is clearly profitable. What this graph is hiding a little bit is that there was a stock split of NVIDIA of I think a 1-to-4 split. So you actually have to multiply this 250 times 4. So that means in the 2 years that I've been presenting this, that the stock price went up times 8 or 9, right? So of course, this is not only because of deep learning. There's a lot of other reasons for this, but a big portion is actually because we really need the computational power for artificial intelligence algorithms. So you see that small dip of 2019, how small it is compared to what we are seeing now. Okay, so the main message is today we have a lot of compute power. And the third reason is that, we just have better algorithms, right? So last year, 3 researchers in deep learning got the Turing Award, which is a very prestigious award. They did some small modifications into neural networks. Of course, it's not just, there's a ton of algorithms that use a neural network. You can think about, okay, we change the number of layers, we change how we update the weights. So there's a lot of different ways of how to improve the algorithms. And these 3 researchers have really been seen as the founders of modern deep learning, right? So deep learning has been around for quite a while, but we have this modern aspect that the last 10 years, we really see groundbreaking results. Okay, so the 3 reasons are data, compute, and better algorithms. Okay, now this was just to set the stage a little bit of what is deep learning, right? So deep learning, we use neural networks. Neural networks get inputs, for example, pictures, try to output something, what is on the picture, and this drives applications like Face ID or self-driving cars that recognize what is going on around them. You may be using it in your company settings. So I'm teaching operations myself. So where can we use this in operations? Well, you could think about forecasting, for example, where we forecast what the demand is going to be. So there's a lot of applications where deep learning is actually being used. But then I got very excited by a specific part of deep learning, and that is named deep reinforcement learning. So this is what I started to do during my PhD. The reason why, and I'm going to explain what this reinforcement learning is, but the reason why is this game. And this is the game of Go. Some of you may know this, depending where I present this. So if I present this in an audience where there's a lot of people from Asia, then many people in the room will know this game because it's very, very popular in Asia, actually. Now, the reason why I'm showing this game is because this game was always said to be very, very complex for computers. Contrary to, for example, chess, where already years ago we had computers beating the best players in the world, it was not possible for Go. The reason is because the board is significantly larger. So you see here that there are 19 by 19 different positions where you can put a stone. Then we have a lot of actions that we can take. So there, if you think about it, there are a lot of different configurations of the board because there's 19 by 19 spots. And on each spot, there can be either a black stone, a white stone, or there can be nothing. Sometimes I ask in class, like, how many potential configurations of the board are there? I mean, are there? And the answer is 3 to the power of 19 by 19. Now, that number doesn't tell you much, but if I tell you that that number is actually more than the number of atoms in the universe, then that will obviously shock you. So many people don't know the magnitude of exponential growth. This really shows how something can grow exponentially. But that also means for a computer, it is very difficult to come up with a good policy, because what does a policy do? Well, a policy tells you, okay, for each state, which action should I take? And enumerating over the number of states is simply impossible because there are so many potential configurations. So we need to build an algorithm that has some sort of intuition about what are good states, what are bad states, and which actions bring me towards better states. So this was a huge challenge, an open challenge for a very long time, until around the time when I started my PhD, around 2016, when some researchers developed the algorithm AlphaGo. There is a really nice documentary about this on Netflix. At least I'm not sure whether it's on Netflix now in Europe, but you can definitely see it on YouTube. So if you just Google AlphaGo, it's actually a really fun documentary to see. And the documentary is about Lee Sedol, who is the world champion, or he was the world champion for several years in a row, playing against the algorithm AlphaGo, an algorithm that was developed by a very big group of researchers. You see here the doubt in Lee Sedol's eyes. Maybe I shouldn't spoil the end of the documentary, but given that I'm presenting this here now, you can expect what happened. So the algorithm actually beat the world champion. Right? So this was a major breakthrough in 2016. Now, how did this happen? So you see the Google DeepMind challenge here. Maybe not surprisingly, Google just bought the people that were making the algorithm. So now this is part of Google. But how did that really happen? Well, it happened using deep reinforcement learning, right? So no surprise in this presentation. But what is reinforcement learning? Well, on the left side, we see an agent. So this is, for example, the player, and the agent needs to take actions. So in the game of Go, an action is you place a stone on the board based on a certain state. And the state is simply the configuration of your board, right? So you have one configuration with a lot of white and black stones, and from there on, you need to take a certain action. Your environment will then play against you, right? So the environment is then the opponent who puts a stone on the board, and you get a certain reward for that. Now, what is the reward in this game? Well, it's very sparse because you only get the reward at the very end of the game, where you either find out that you lose or that you win. So very sparse reward. But through trial and error, through constantly being in states and taking certain actions, the algorithm actually learns a policy. So it learns how to play the game of Go. Now, in this loop, what is embedded, and that's why, so this is just pure reinforcement learning on the left side. But if you embed in this loop a neural network, then you get deep reinforcement learning. So the idea here is that the input here is the configuration of the board. It will pass all the layers of the neural network, and you see there are some convolutional layers, some fully connected layers. So this is really a very complex neural network until in the end, the actions of what you can do will be chosen or by the algorithm. Okay. So this is the core of the algorithm. There's beautiful papers about this in the magazine Nature, but they are very technical. So I'm going to try to avoid going into technical discussions here. But if you have any questions, feel free to just use the chat or stop me at any time. But I don't think there are a question. Oh, there's actually one question here. This is how text captcha stopped working. I think the question was already 14 minutes ago. I'm sorry for missing this question.
Yeah.
So I can come back to this. So in what context was this? This was regarding supervised deep learning, right?
Right. Yeah. Right after you were looking at the Tesla cars, you mentioned something about the layers, and you were just looking at numbers written like in different shapes. They didn't really look like text numbers, you know, like the computer writes.
Oh yeah.
So
okay, so the link between deep learning and captcha is actually really interesting. So and I often, like, if I have some more time, I explain this to students, because if I would ask you guys, like, okay, why do we have captchas? So you know, a captcha, for those who don't know, it's this, you know, at the end of the or like if you go on a website, it asks you, can you please identify the pictures where there is a boat, or can you identify the pictures where there is another car? So this is something that we typically don't like, or it can be text and you have to type the text. It's examples that we typically don't like. Now, why do we have these? Sometimes I get the answer, well, this is to get robots off the website. And that's true. That's true, that was the original intent. Now, then why do we always get either text messages or pictures of cars or pictures of traffic lights? Is there someone who actually knows the answer to this question? You can use the chat if you want, or just speak up. That's totally fine. To train autonomous driving, yes. So there's people in the room that know why it is. So specifically, what's happening is that, you know, to train deep learning algorithms, we need millions of data, labeled data samples. Now, if you go to San Francisco, you see these cars driving where they are just filming the environment. So they basically generate so many data points. Now, this is unlabeled data, so we can't train an algorithm on that. So what is happening is that then people are really doing this labeling, but of course people are very expensive. So what they do is, well, they basically hire people that do it for free, and these people are here in the room. It's basically all of us. So we are actually labeling the data for companies like Google or Tesla, or, you know, any company that needs labeled data. So what we are doing is we are learning them to, or we are labeling the data to detect where traffic lights are, where buses are, where trucks are, where bridges are. So we're labeling the data such that these neural networks can actually learn what the labels are to then be applied in autonomous driving. Yeah, so that's actually the right answer. So the link between supervised learning and captchas is indeed very apparent. Really nice comment. Okay, so back to deep reinforcement learning, we have the reinforcement learning framework and the neural network. And this combination seemed very powerful. Now, I am in operations, and so I did my PhD together with a company in fast-moving consumer goods, and I was specifically looking at inventory settings. And I got very excited by this technology. Now, of course, I was doing a PhD, so I had to stay within the scope of my research topic. So I tried to find synergies, and it turned out that there was actually very big synergy between the game of Go and what I was trying to do. So it appears that many problems in inventory control and in operations in general, or in the world in general, suffer from the same problem as Go, which we call an exploding state space. It means that if you make the problem larger, it gets very complicated to solve. And most of the heuristics that we use, so most of the decision rules, are problem dependent. So they work well for one specific problem, but you can't really use them in other settings. So let me give you one example. The problem I was working on in the fast-moving consumer goods company that I was working in. So they have a plant, a factory, and they have to supply a warehouse. Now, they have two ways of doing this. They could either send a truck, which has a higher cost, but a shorter lead time, or they could take a slower transportation mode, which has a lower cost, but a longer lead time. So there's this trade-off going on between do you want to go fast or slow for different costs. Now, it turns out that this is a very complicated problem. I know this really looks like a toy problem, and you could think like, wow, it's very easy to solve, but it actually is not. So we have been doing research for decades. We still don't know how to optimally replenish the warehouse. So that was the scope of my PhD. Now, where do these things come together? So where does reinforcement learning come together with this inventory problem, which I just described? Well, on the bottom left side here, you see the inventory problem, and we have to model this as a reinforcement learning problem, right? Where we have this agent that can learn how to take actions in a certain environment based on the state, and it will incur rewards along the way or maybe in the end. So this is the reinforcement learning framework. Well, what you see here is that the state of the system, we can model it as the on-hand inventory. So that means all the inventory that is currently already available in the warehouse, and all the pipeline inventory. So this is your inventory that is in transit. So it will arrive in 1 day or in 2 days or in 3 days. So we typically know where our inventory is. So it is on the way, but it's not there yet. So the state space of our problem is this, right? So it's your pipeline plus your on-hand inventory. So just like in the game of Go, where you have your configuration of your board, my agent sees what's the configuration of that part of the supply chain. So where are the inventory levels? Or where are the inventories? Like, are they in the warehouse or are they in transit, etc. So what are the actions here? Well, rather than putting a stone on a board like in Go, we have to decide how much we order using the truck and how much we order using the train. And that is what the agent has to do based on the state. And what are the rewards? Well, you could add a lot of rewards. Typically, I model all the costs of the company, which are inventory costs, so typically holding costs, backlog costs for service level, transportation costs for the fast modes, transportation costs for the slow mode, etc. But the cool thing is you can model the reward function like you want it to be. So it really depends on the specific company, which reward function you will use. So you see that, you know, this is, it's also called the Markov decision process, that we can model the problem of the company similarly to the game of Go. And that was the starting point for my research, because then I said, okay, now I can go into the computer science literature where there's all these beautiful deep reinforcement learning algorithms. I can take them, I can plug them into this dual transport mode problem, and I can just let the model train. So that's what I did. It took me a long time to figure out what I was doing, or not what I was doing, but to figure out what the algorithms were about, which ones worked well, etc. Ultimately, I ended up with this one. So it has a monstrous name: asynchronous advantage actor critic algorithm, simply the Ac3c Algorithm, where you have a lot of learners that are operating in different environments. So you have to think about this as simulation environments. So I model this little problem as a simulation environment. So there are certain inventory levels, and you can just play around there, learn through trial and error in a simulation world. There are several workers doing this in several environments. They each always see as input the state, which is your inventory vector. They have a neural network. They have a neural network which proposes which actions to take. So the policy, that's the actor of the model. And it also outputs a critic, which is the basically an estimation of what the cost will be if you follow the policy. So through trial and error, by just simulating a lot of times, the idea is that we update the parameters of the network in such a way that the model learns how to order well and make good estimations of what the costs are going to be. So that's what I did. And I found out that, this is a training plot. So what you see here is that the longer you train, the performance of the model gets better and better. So the blue dots here is a training curve, is a training performance during training. And so and the red curve is basically the best model that we find along the way, and that's the one I save to then deploy in production. So this is an example of a training curve. It took me quite a while to figure out how to get the model learning. Right, there was a lot of tuning that I had to do to get it to work. But once it worked, it as you see, it really had it developed very good replenishment policies. And I was very excited at that time in my PhD. So we wrote a paper about that, which in the meantime got published. So this was the main result. Now, I also applied it on real data in the consumer goods sector. So not just on a toy problem with made up data, but I also looked at, okay, what is the actual demand of the consumer goods shipper? So it was a producer of well, products like shampoo, etc. So I had the historical demand. I fitted a demand distribution on that demand. So here you see the typically in consumer goods industry, we often see gamma distribution. So this is a fit of a gamma distribution on the data. And the cost functions that we used was a very specific one for the company, where every time you order a truck, you have a fixed cost because the truck actually has to come to your warehouse or to your plant. And then per unit that you put in the truck, you also pay a variable cost. So the idea is that per pallets that you put in, you have to pay a little bit. And then you create this piecewise jump function. Every time we order a new truck, we have to pay this fixed cost. So I tested it on data between France and Italy. The lead times were 4 days for using the truck and 7 days for using the train. And I, as you see here, this is an example of one SKU, so one product, which had a very high volume. So this is in pallets, right? So 25 pallets is approximately one full truck. So it's really like one of the higher volume because they had on some days they had just full trucks of that specific product. And it's a stationary problem. So that means that even though there's a lot of variability, there's no trend in the data. So it's not going up or down on the long term. But this was just one example. So I'm also working with other companies now where we're looking at totally different cost functions and demand data. Demand data. Okay. Now, so we found that it actually worked, which was great. Now, there are some things that I do want to share. It is that tuning the algorithm took us a long time, right? So we adopted first of all, I played around a lot with the model. So I was doing a lot of prototyping, where ultimately I ended up fixing most of the parameters of the model. Now, what are these parameters? You could think about it if you have a neural network, you have several layers, but how many layers, right? This is a hyperparameter of the model. Like, will you choose a neural network with 2 layers or one with 3 layers or one with 4 layers? Like, these are design choices you have to make. There are a lot of other factors like the learning rate, which means, okay, if I update my weights, how much will I update the weights? So these decisions are, they're left up to the discretion of the coder, which in this case was me. So there's a lot of things you have to choose. So I fixed most of them, and then I did a random search on the remaining parameters. So basically, you'd say, okay, I have a range. For example, the learning rate can be on a certain range, but you just do a random search over that range. What do I mean with random search? Well, so you pick a certain set. So let's say, okay, I decide on 4 layers with a certain learning rate. Then I basically have a model that I have to train. I put that into the cloud, right? So in Google Cloud or in Amazon Cloud, it doesn't really matter. I use university servers actually. So you train the model. It takes a couple of hours, right? So a couple of hours, it needs to simulate and it needs to learn, and then you need to evaluate at the end whether the model is actually a good model or not. So that's what I did. And then lastly, so all these points you see here are evaluations of the trained models. And you see some trained very poorly, the red models, but some, the area in the bottom, the blue points actually trained very well. And that allowed us to kind of identify, like, what is the best structure of your neural network? What are the best parameters to solve this specific problem? And that's something that, of course, then companies can use if they start, that they don't need to do all the work that we did. Okay, so I am wrapping up here because I just have 2 minutes left. So the conclusion of our of this work on deep reinforcement learning was nuanced. A great result that we found is that this deep reinforcement learning technology seems like a very promising one. Why do I say general purpose? Well, we didn't just test it actually on one specific problem. So I tested it in this dual transport problem. But then I said, okay, what if I take exactly the same model with the same parameters, and rather than training it on this transportation problem, I train it on a multi-echelon problem, which means that you don't look at one part of the supply chain, but you add an additional part of the supply chain. So you basically have so you have a factory, a big warehouse, and then a small warehouse, right? So your supply chain gets more complex. Again, same type of modeling. Turned out that it actually continued to work well. So that, because of that reason, like, it is a technique that once you have it, you can apply it in different parts of your supply chain, which is great. Especially when you don't have problem-dependent heuristics. So think about it as follows: like, you have a new supply chain setup. So how are you gonna develop a good replenishment policy? It's not so easy. You could, sit together with some managers that have a lot of experience about the problem and come up with a replenishment policy heuristic. But if you don't have a good one and you have specific company dependent settings and cost functions, then this is not so easy. So that's why having a learning algorithm that then can do all the work for you could actually be a very good alternative. A downside is that it remains a black box. So that means that the policy that comes out can perform really well, but the policy itself is not very interpretable. So we don't know exactly why in certain situations the algorithm is taking certain decisions. Just like with the game of Go, the algorithm AlphaGo did things that people thought were bad, but then ultimately ended up leading into new strategies. So we can learn from that, which is great, but sometimes we just don't know why the algorithms are doing what they are doing. And of course, to adopt this method in practice, this really limits it for many companies. And the last part that I want to conclude with is that the computational efforts to train deep learning algorithms remains big. So we had cloud servers, etc., but you really need that. This is not the type of algorithm that you can just train on your regular desktop, basically. So I think I am spot on time. So I'm from Belgium, so we try to stick to the timings as much as we can. So with this, I would like to thank you for your attention. Thank you for being here, and I would like to open the floor for questions. So I haven't received any questions during the talk, so that's great. There's still 15 minutes left for questions, so feel free to use the chat or to just speak up in here. So thank you very much for your attention.
Joran, that's wonderful. Thank you very much. I think you have already one question in the chat. Yeah. That was asked 5 minutes ago.
Okay. So it was easy for the algorithm to learn and react with changes we had with COVID. Wait, impact in terms of demands. Yeah, okay. So this is a great question. So what is the impact of COVID in general on companies and their supply chains and their operations? Well, it's true that if you train your algorithm on certain data, and that data is not representative for what's going to happen in the future, then you're going to run into problems, right? So, and I remember when the COVID pandemic really hit, like in the beginning of 2020, is that a lot of people also, there were a lot of seminars going on in supply chain management, telling like, okay, what should we do now? Should we trust on our systems or not? The answer was that, that was really the time in the beginning of the COVID pandemic to really, sit down together, look at the systems, have human interaction there, and see where we could still trust the systems and where not. So if you would just train an algorithm on data that it doesn't have such extreme events, then no, it's not going to work well. Now, on the other hand, you could also create a simulation engine where you include these extreme events. So if you want to have a more robust algorithm, then that's something you can do. So this is yeah, this is a little bit of an answer towards your question. I hope it answered it sufficiently.
Is that what happened? Did people actually sit down and check the algorithm to see if it worked?
I think looking at how many issues you had the last years in supply chains. So we have a major shortage in chips at the moment. We we have huge delays in huge delays in production, etc., because there's a shortage in raw materials. Shows that probably not, right? So we have been really going into lean inventory management the last years, trying to reduce our inventories as much as possible. I remember when the pandemic started that all the professors were screaming like, be careful, be careful. This is really like the fact that everyone just halted their operations. We said like, this is really going to run into problems. And the fact that some companies had to really shut down some plants for a while because there's just no raw materials anymore shows that probably we didn't do enough. That being said, it was a very extreme event for supply chains. So even if we had seen it coming, it still is not so easy to just cope with all the additional variability in the supply chains due to COVID. So it is just a very difficult. Like variability is really the enemy of supply chains, and COVID brought so much variability, and 2 years later we still see the impact. And for me it's great because I can use it in my supply chain classes, but I can imagine that if you're working in companies that it's really painful. Who is your customer, end users or supply chain softwares? Who wants to add your algorithms? That's good. So so I'm working with the companies themselves, right? So I'm working with the manufacturers or the e-commerce companies at the moment, and I'm really trying to develop algorithms that they can use in their systems. It's interesting because when I wrote my paper, at the same time, a couple of colleagues wrote a similar type of paper in the US. I got along really well with them, and they ended up working for SAS. SAS is the statistical software company, and what these guys are doing is they are actually implementing the algorithms in SAS. So for them, the answer would be more like, we're working with the software companies, while for me, the answer is more like I work directly with the companies, but I do work with the people that have access to the systems and really change the systems. Another question, does the difficulty of tweaking the algorithm have anything to do with finding and escaping local minima? Is there any practical way to do this? What was the accuracy? Yes, okay. So so many of the problems that we solve, they do have local optima. So the specific algorithm that I showed you, the A3c algorithm, has a stochastic policy which randomizes the actions. And the idea is that because you have a stochastic policy, you take random actions, so you sometimes end up in states that you haven't explored yet. At the same time, we have parallel learners that learn in different simulation environments, so in different areas of the state space. And this really is to avoid that you converge too quickly to local optima, because there are other methods that are more stable, so they have better convergence properties, but they don't converge to the global optimum, but to the local optimum. So you're totally right that we need to be very careful for that. So the algorithm does that. Now the difficulty in tweaking itself is partly because of that, because you need to encourage exploration in a way that you want to explore enough to be able to find the best solution. but then you don't want to explore too much, because then you will, once you learn something, then suddenly you transition again towards a very bad solution. So there's this really like fine area where you have sufficiently exploration to learn new things. But then once you have something that works well, then you also want to learn in that environment, and you don't want to go too far away from it. So but yes, this is really a trade-off that one needs to pay significant attention to. Yeah. Thank you. These are really good questions. Do you think that deep supervised learning will be compatible with transparency or explainability? Yeah, so in deep supervised learning, there is actually a lot already going on with interpretability. So there's some books about that as well. I myself must say, because I don't want to say that I'm an expert in everything, and on the interpretability part, I'm not the expert. So I can already say that. That being said, I may become an expert at one time, because many companies are asking me for more interpretability. But there is a lot of research going on there, right? To try to, and this also comes from applications, right? So if you have, for example, self-driving car that ends up in an accident, then you want to know, okay, why did this happen? And insurances may want to know why, and so that because of that, like we probably need some more effort in trying to make the nets as interpretable as possible. That being said, there's also here a trade-off between how performant is your algorithm. If you make a very complex neural network, then ultimately you will have to give up a lot on interpretability. So it depends a lot on the application. I think in supply chain management, interpretability is important, but maybe not as important as in other applications where there's really lives at stake, for example. But yes, there's a lot of work going on in trying to make the outputs of neural networks more understandable for humans, and yeah, it's ongoing research. Is there still a question? Rafael, do you have a question? Because I see your hand is raised.
Yeah, sorry if it's kind of shallow. I'm a first year, so I don't know much about the subject. But what language did you write this on, and what kind of what
libraries?
Are you? Yeah, like where did you get all the sort of training to start writing code like this and algorithms like this?
Yeah, very good question. And maybe it also transitions with what Professor Felipe will say afterwards. So to answer the question, like, okay, where did you code this? What language did you code this? I did everything in Python. So Python is my go-to language. Sometimes I code in different languages, but for machine learning and deep learning, I use Python. There is great libraries. So in my so I'm actually teaching this as well at Católica. So when I'm teaching deep learning, I'm using both Python and R. And the main libraries that I'm using is Keras. I find it very intuitive. There's a great book about it. It's actually called Deep Learning with Python or Deep Learning with R from François Chollet. Great book, explains very well what deep learning is and how to code it. So it's with coding examples. So if you want to start, I would say read that book. It's actually freely available, but you can also buy it and read up on it. So that's a great starting point. How did I do it? Well, I really started from scratch, to be honest. So I just had a goal. I wanted to get somewhere, and I had time during my PhD to study, and I studied it myself. It is quite intuitive once you get the hang of how to use these libraries. Yeah, and if not, then of course you can. You're very welcome to join our classes. So we're having a ton of new programs, and deep learning is being taught in several of the programs. So yeah, so feel free to connect on this one.
Joran, I think this is a great way also to close seminar. I have just a couple more minutes before we close exactly on time, because I'm not Belgium, but I'd like to be in terms of ending on time. First, I'd like to thank you for what you just did. It was we know it's an amazingly complex topic, but also a topic that we know will change business as we know it and will transform companies and will make new industries. And your ability to explain very complex issues in a very simple and practical way that we could understand is amazing, and only people with deep understanding can do that. So thank you very much for your contributions in this seminar. I also would like to follow up that in addition to Joran, we have an amazing group of faculty in data science, artificial intelligence. Many of you already heard from Miguel Matos. We have also other people who works also in issues with telecom companies and customer churn, among other topics. We have other people working on retail issues as well, on smart cities, how to organize a city to optimize certain outcomes. So we have really an amazing group of faculty, international faculty devoted to this topic and working regularly with companies and using the latest technologies. And of course, we are transforming that expertise into training programs. One that I would like to highlight is our Master of Science in Business Analytics. We launched it last year. We have a great class of about 30 students working really hard with all of these techniques that Joran described. And I'm sure the program is not yet ranked because it was launched this year. It will only be ranked in 3 years, but I'm sure it will be one of the world top programs in business analytics, like our finance and management programs already are, because of the quality of the faculty. And this is for a pre-experience masters, so for people who finished the undergraduate or have just 1-2 years experience. For executives and people with more experience, we have 2 programs that are not new, where they have them in a couple of years, but we'll restart soon. One is Artificial Intelligence in Business, that starts the 31st of January. It's a program more at the strategic level for executives and managers who want to understand how to use artificial intelligence in their business decisions. Has a great set of international scholars led by Miguel Matos. And then we also have another program called Data Science for Business, beginning on 17th of February. And that program is really applied. You actually have to solve practical problems using some of these programming technologies. So you will learn by doing in this Data Science for Business program. So it's highly recommended to have a deep sense of what it means to develop some of these algorithms and apply them in real practice. So those are programs that you will have to work, especially the second one, a lot, but really will give you a level of insight and expertise that is, I think, very, very special because of the faculty we have at Católica. So this is what I would like to leave you with this idea that as a community of learning, this is a topic that we are investing a lot, data science, artificial intelligence, and we'll continue doing more programs and more seminars on this topic to bring the best expertise to our community. With that, I would like to thank all of you for joining us for this session, and in particular, to thank Joran for his insights and contributions. And maybe as we close, maybe we just open up our mute and thank Joran for his great insights, and then we'll say farewell to everyone.